take some crayons and break them into pieces. So here's what your test setup looks like. So first, there are some rules. Your package cannot be taller than 3 inches, and it must be inside this chamber. The materials that you can use to build your package are some aluminum foil, any kind of styrofoam material, plates, styrofoam cups, a plastic solo cup, some paper, and some tape. You can use any of these materials to build whatever kind of package you want, as long as it's not smaller than 3 inches and it fits inside this chamber. Well, I'm going to try and make a package and see what I get. So here's my design. It's pretty simple. I didn't want to use the aluminum foil or the paper because it was going to be added weight, so I used the plastic solo cup for structure and some styrofoam. It's a good heat insulator. It's reusable. So here's how you put your package. Make sure your crayon fits inside your package. Make sure your package fits inside the chamber. And once it's in there, all you have to do is take the hair blow dryer, stick it in the chamber, and heat it up for 30 or 45 seconds.
Yeah, so, yeah, so unfortunately the end result of that, I wanted to do a further explanation, but it got deleted throughout the process of editing, and with the little limited time I had, it was, unfortunately I couldn't get that back. So what had actually happened with that was, I made that simple design to show the flaws in that design, and just to get an idea of where students can get started. So my design challenge is pretty open-ended. It's open-ended in that there is no basic model that students need to follow in order to build this kind of package. I left that pretty open-ended. It doesn't have to be a box. It doesn't have to be any shape or size. But the one thing that makes it a design challenge and not just out in the open, I have no idea what to do type of problem, is that they are given a certain list of materials that I list in this packet here. So they're pretty standard materials that any teacher, whoever instructor can get their hands on. Your aluminum foil, like I mentioned, styrofoam, paper, cups, tapes. So a lot of these aluminum foil and styrofoam are more the extreme materials that students are supposed to use so that they can understand what conducts heat and what is a good insulator. So when we delivered this design challenge, one student was really impressed me by knowing that right away aluminum foil is a really good heat conductor and styrofoam is a good insulator. So some of you guys may wonder why I would even put aluminum foil in this design challenge. It's so that it is possible that you can use it, because just using styrofoam, it is hard to manipulate. So then that introduces a new element of forcing students to think about how to layer the different materials so that it can be a better insulator, so that it can protect the crayons better. Because styrofoam, unfortunately I couldn't show it in the video, but when you're hitting it with a hair blow dryer, it actually shrinks. Kind of similar concept to like how a shrink wrap works. And so because of that, they had to compensate that by using various materials. So it was a very successful challenge. And then another element to really make it a challenge and slightly competitive is to have a weight component to it. Because let's say a student did make a package that did work. They opened the package and saw that the crayons didn't melt. Then what? So we added a component. I had a component where they had to measure the weight of the package, and they started to make a list every time they tested it, and when it was successful, they would write a weight, and then their next goal would be to reduce that weight and not let the crayons melt. So it was a really positive, fun, encouraging, slightly competitive environment in that classroom.
John, I got a quick question.
Yes.
Why do you use the vocabulary packaging?
Packaging? Something just so that students can relate to, because they had to enclose the crayon all the way like a package. So,
does it relate? Is that a good description? Does that relate well for your research?
It relates in a very abstract way. So in Novamin is a protective layer but it, it's, so with that, and like I said in the video, like that inspired me for students to build something that protects, something, which was the crayon in this case. And so even though obviously this isn't anything like a tooth or anything like that, just the concept of, preventing things passing through is very general in the way that I try to relate it, so.
I think that's fine. I think that the vocabulary is a little misleading with just packaging, because
Okay.
the packaging is how you send things in the mail, or different things like
Okay,
that.
yeah,
So I think protection,
okay, yeah,
protective structure, shielding,
okay,
different things like this that might relate more to the concept of shielding your teeth from sensitive things like heat.
yeah.
Okay,
Like,
so go right ahead.
yeah, I will, definitely keep that in mind and make adjustments. And also another, component that students have to think about was the fact that airflow was coming down one way. It was coming, from the top to bottom. So some of the students, they would use styrofoam, but because they didn't use it near the top of their, package,
Yeah, that's
yeah.
fine. Don't worry.
Like they, and and they flipped it around, the crayon still melted, and so students had to, improve that, look at that, and figure out why. So it was a fun design challenge in that. So overall, taking away from this, I think first off, I took it for granted that I got the kind of education that TEK8 did, but on a daily basis in middle school, which has led me, hugely influenced why I want to be an engineer. And I took that for granted, like I almost, believe that everyone, in America has that basic, education, technology education, but unfortunately that's not true. It is not basic. Only, certain schools have it, which is why we have programs like TEK8. So I think it was an eye-opening experience for me, realizing that there are unfortunate students who might go through their entire K through 12 education and not ever have any kind of concept of doing these design challenges. They'll know how to take tests, study, learn materials, but to learn, think critically is something that I think that in K through 12 education is lacking. And so having engineering design challenges like project-based learning, which is a lot of vocabulary that people use in papers, is something that was really important. It was cool to be part of that. And then also to be on the other side of things. So I used to be, I remember being those 8th graders, doing these types of projects. So to be on the other side teaching was also interesting. It was really fun. But yeah, I would love to keep doing something like that.
Perfect, great, thank you. Who wants to be next?
I'm next.
Yeah, okay. Sorry, Jeff. That's okay. Jumping on that one right there. All right.
No problem. No problem. It's really fun. There you go.
Thank you.
There you go.
You don't want to do that. Help not. Did you model that playing in SolidWorks? Or did you just do it?
I've stolen.
That's like, I don't know if you remember the animation you made in my video. With the shine the cylinders and the
yeah.
injection. That was definitely fun.
Really, I wouldn't have guessed.
I can do
Design
it.
an engine over
I
the
can-
weekend.
And while
I can-
Josh is getting set up here, if I could make a shameless plug for the student branch of the American Society of Engineering Education. I haven't seen enough of you folks participating in the ASEE student chapter. I hope next semester you'll watch for the emails on that and become part of our ASEE student group.
We have an outreach venue that takes them into some Columbus City Schools classrooms. These are 9 through 12, not middle school, where they have kind of a design challenge venue. And then there's a return visit that has they did this to Northland High School last year, has the students come here to OSU and they have sort of a design challenge set up for them here, and a tour and some other things, so.
We'll have some interesting speakers and a regional meeting up in Detroit this spring, so something to keep your eye out for.
What was the acronym one more time?
ASEE, American Society for Engineering Education.
President is a scholar to your revenue, Jack.
Really?
No, Chris Wallace.
Chris
Wallace.
Oh,
He
yes.
was-
Chris is the president?
Yeah, Chris is one of our officers.
Yep. Or maybe he's president. Something like that.
I saw him today in CSO.
Sorry, I'll do a video first and then talk about my thing.
Right, which one is it needed? Or,
Let me just grab my stuff over there.
That's fine.
Sorry.
thank you. Some people are already showed. Yes. So more than you said.
This picture you see in America.
Team. One of the soloists. He floated that first. He just made it up.
Do you sing?
Huh?
Do you sing?
No, the video is on
Funny people.
It's a video of you have, and you can just like by myself. 'Cause it's like-
Wait, excuse me,
Oh.
I have a question just on the design challenge. Did you guys have a budget that you had to work with?
Our own pockets.
Your own pockets? Because the theme of cereal boxes was so consistent. It's like all your roommates, and it's fun, give me a box, give me a box.
Part of the main focus was so that it was cheap, so people could reproduce it easily. And a lot of us had like wooden structures as our first like design challenges,
Yeah,
and they changed into Jax is a great example. He had this awesome wooden setup, and
Masterpiece.
yeah, it was
Feet long,
it was
wooden ramp.
fantastic.
right.
Now it's a cereal box.
I built a 1.5 square filter that they interacted with for my first design challenge. It took me about 6 hours to make one.
Oh, really, wow.
Okay, I'm gonna start. My name is Josh Westino. For my video, I have an intro, and then I'm gonna talk about my design challenge in the second half. So.
Oftentimes, engineers have to pick the right materials for their designs. Some materials include ceramics, glass, metals, and polymers. So what is a polymer? Poly means many, and mers are molecules. So many of the same type of molecule connect in a chain called a polymer. How small are polymers? Polymers are smaller than ants. They're even smaller than the width of a human hair. They're tinier than cells. And now we're at DNA, a biopolymer, or a polymer found in living things. Plastic bags, hair products, styrofoam cups, and credit cards. These all have polymers inside of them. What properties of polymers are valuable? Many polymer-based products can be folded and then unfolded back into their original shape without any damage. What are some other properties? Many polymers are strong. They're light. And they're flexible. For example, parachutes are made out of nylon, a strong, light polymer that allows the parachuter to land to safety.
My name is Joshua Westno, and I study chemical engineering at The Ohio State University. Like you saw in the video, parachutes are often made from polymers. But what would happen if you use a different material? Let's say aluminum foil. Well, aluminum foil would be a bad material for parachutes because when you fold aluminum foil, it breaks very easily. In this design project, you will design a parachute that can meet the following 3 goals using this testing apparatus. Goal number 1. Take your parachute and fold it into a small backpack. If you are able to unfold it and it doesn't break, you pass goal 1. Goal number 2. Blow air into your parachute for 10 seconds to test for strength. Release your parachute and count how long it takes to land. To make a good design, you must use the engineering design process. Step 1 of the engineering design process is identify the problem. Step 2 is design your parachute. Step 3 is build your parachute. And step 4 is test your parachute. To make the best design, though, you must repeat this process 2 or 3 times. A good design will be strong and will also float in the air for a long amount of time. Now it's your turn. What will you design?
Okay.
Love it.
So, going through the packet, I kind of followed templates pretty closely, but in the classroom, what we did was we had a prototype, but the prototype was meant to fail. So we made them do an aluminum foil parachute. So basically, when they folded it into their backpack, which I don't know where the backpacks went, so sorry. You crumple it up, and then they realized that it broke. So they realized, well, aluminum foil, that's not the best material for parachutes. So we had them do that, and then we had them work in pairs. And so basically, we asked them questions like, why did the aluminum foil parachute fail? And that would get them thinking about what materials are good for designs. We didn't really talk about aerodynamics too much, but I kind of when I was going around, what shapes do you think would be good for your design? And this is the test setup. Pretty much how I made this, I just put 2 of these called Gorilla clips?
Binder clips.
Binder clips, okay. And I put one of these paper clips on it. And this is an example of one of the designs. And so here's a Lego man. And so basically I just attached the Lego man onto the paper clip. And they'd test it for 10 seconds to see if it was strong enough to withstand the force of air. And then they would blow it in the air to see how long it would float in the air. And I kind of have, in the design project packet, I have a layout of the prototype with different pictures, step by step. So that takes them to the process of what they have to do. And then I tell them, now refine your prototype. And that's pretty much it for the packet. Any questions? Yes?
Did you sell the bag as a balloon?
Wait, what?
Did you keep the bag as a balloon? Or did you change that?
Oh, yeah, I kept it as a balloon.
Okay.
Yeah. I don't know where those balloons went.
It's somewhere in our box.
It's somewhere in there. I don't know. But I have it here. I have a PowerPoint real quick. It's really short. That's it. Okay. Next slide, please. Okay, so some of the challenges I faced were, 1, translating engineering into something that middle schoolers can understand, or and science concepts. Another big challenge I faced was controlling the classroom. I know the first day they got really ruckus and they were getting in front of the camera and hi, and they were just doing stuff like that. So, and then developing an effective design challenge, because we had a time constraint of an hour, so that was kind of hard. But I like this picture because it shows what a good teacher can do, and yeah. Next page. I think this picture is pretty funny.
That was Josh on day 1.
That was almost
day
day 1.
Josh will return.
But this is an example of how I talked about like polymers to the students. So next. So I said minimers, which are these little molecules. Next slide. They can attach to form a long chain called a polymer. Alright, next slide. Next slide. So what I've gained from TEK8, communication skills. I did not know how to describe polymer to an audience, as you guys all know from my first presentation. I think I learned a lot about what it means to be an engineer, because when you make the design project packets, you have to think like an engineer to think like how can you make this very open-ended. Teaching skills, definitely learned that. I'm teaching going to be right here. Yeah.
I'm so proud of that picture.
Is that the sweet one that's on Facebook?
Yeah.
Okay.
And that, I think, is it. Oh, would I recommend this class? Absolutely. I'm actually looking forward to what future students do in this class. Thanks.
Awesome.
Yeah.
All right, thank you. Okay, great. Who would like to go next? Randy?
Sure.
All right, go ahead. Randall.
You're not supposed to call him Randy, remember?
I know, that just brings up.
Did you shoot my email?
I did.
I signed it Randy for you.
Did you sign it, Randy? Oh, that's funny. Randall, he surprises you at times. What's up? There it is. Good job, Josh.
Okay.
I feel like everyone has an 8 a.m. exam.
Yeah.
Yeah, so that's what I was saying. Every day.
I mean, I'm working.
Yeah. Exactly. And you make knowing that you can't use all these material events.
It might be interesting.
I know, that just.
Or this is like an old version of the
I'm like, oh, what is the birds name?
For your background, is it meant to be about
I would never really say that, but you know, hey.
Uh-oh.
Not me.
It is.
Are they?
Yeah, or not really talk spills, just over fertilization. Oh, did I forget to change something?
Yeah, it looks like it's the
it's the
biobot or
example.
the.
Oh, which one did it? Oh, background?
Yeah.
I changed that one? Okay. Oh, it's not supposed to be that
Okay.
Thank you.
Hi guys, my name is Randall Berkeley, and I'm a civil engineering student at The Ohio State University. And this summer, I did research at the Biological Sciences Greenhouse. And our goal for the summer was to build 2 identical rooms, the one you see behind me. The reason we built these rooms was to help us determine the path that plant roots take depending on different environmental factors or the variables they may encounter, such as nutrients, sunlight, or water. We did this in a controlled environment such as a greenhouse. The reason we did this whole experiment was we think it can help us prevent pollution. So, for starters, have you ever seen a lake or a river like the one behind me? There's these things, these green things, they're called algae blooms. They come from runoff from over-fertilization in farms. And what happens is when the algae bloom gets there, it takes up too much of the oxygen and nutrients, and it can kill some of the living organisms, such as the fish that live in those lakes. So the reason we did this in the greenhouse was, like I said, it's a controlled environment. So what a controlled environment helps you do is it gets rid of confounding variables. These are the variables like sunlight, water, and nutrients that can be different in other places. So let's say I have a plant. Let's take plant A, which is on my right. Plant A is bigger than plant B on the left, and that could be caused by many different things. So if I told you that I gave more sunlight to plant A as it grew, that might explain why they're different heights. But now let's say I gave plant A more sunlight and water. Now, how do we know why it grew bigger? Was it too much sunlight or too much water? So this is what we can control in a greenhouse, and that's why we built this room. It's designed with a rainfall simulator and tanks which simulate the soil. So now that you've learned a little about controlling the environment, it's your turn to build a greenhouse. Help remove confounding variables. So for your challenge today, you're going to water 2 plants evenly by building a rainfall simulator. You can build a rainfall simulator out of any of the materials your teacher has provided for you. Once you've designed and built your simulator, you're going to bring it up to a test setup, similar to what I have up here. All mine is 2 PVC pipes with notches in them. So that way you can raise and lower the shelf to different heights, depending on the height of your simulator. And in this shelf, there's 3 holes, so you can place this funnel in different locations to help you with your design. So what I did is I made this is my rainfall simulator. There's a couple Dixie cups cut in half and attach these rulers, because when you place it in the test setup, you're not allowed to touch it. So once it's in there, you're going to pour the water into the funnel and see how well the water evenly distributes.
Okay, so as mentioned, my background has nothing to do with toxic spills. It has to do with over-fertilization. I can fix that later. But I pretty much I just followed the outline. So my design, we originally didn't go in with this test setup. We kind of just let him hold it. And Howard noticed that it was kind of easy to just change how well it worked. So you could like tilt it one way and then one side worked, but you could have a perfectly fine design. So we had a couple ideas. This was the easiest one for what I had like at my house. It was just 2 PVCs. I cut them in half and just made some notches. You can raise and lower it. No funnel fits in here. What else? That's pretty much it for mine. I wanted to talk about, you guys all talked about like one specific thing, so I tried to focus on confounding variables, kind of the engineering design process, because we didn't do a whole lot of research work, like most of you did. There wasn't really, we were trying to see if something happened, and we still don't know if it happened, so. So that's that. For what I
When you
get.
say we, you mean your research?
The research advisor. There's still I worked with a grad student and his honors thesis, or his graduate thesis is on it, and it's not turning out the way they hoped it would, so it was a good thing I didn't teach them that I did that. So, what I got out of the class, my mom's a middle school teacher, and I always wondered, like, because she teaches the same thing year in, year out, and I always wondered why it took her so long to do some of the stuff it did. And just like putting together a 10-minute presentation, and all of a sudden it would take an hour, it made me appreciate more what teachers actually did growing up. So that was one thing I got out of it. The other thing, I have to agree with Nate, I was a sports counselor at like camps, and of course the kids all love to come in and play around, and like they always enjoyed me being there and all the counselors being there. So that was fun. But to see that we could take engineering, which not everybody finds fun, we do, but there's not a whole big population who does, and the fact that the kids can still love it, like our kids came running up and they all wanted to say hi when we went to the showcase. That was really cool to see how we can make them enjoy engineering. So.
Great, thank you. Roland, go right ahead.
I'll pass them out.
Okay.
Can I ask another question?
Sure.
I really think we were talking back here just now how making projects that are interesting inspire kids to learn and be excited about concepts they might not be interested in. But I'm interested in your opinion about the relational side of the experience you had. So when you were working with the students, do you think the fact that you were talking to them, that you were kind of engaged and asking, that had an impact, or was it just the design challenge? Or what was the role of relationship in what you saw happen, like the 2 camp counselors talked about? Yeah.
I think that it's definitely a mixture of the two. And I think that was really illustrated for me by the fact that the very last week, so we'd been in there 6 weeks, we had 2 new students in our classroom, and they still liked the design challenge part, but they didn't, I don't know, we hadn't established that respect or that repertoire with them yet, and so they were acting out a little bit more, they were a little less focused than the other students. So I think it was a mixture of the fact that they were interested in the design challenge and the fact that they knew that we cared and we were coming back and we were putting a lot of work into this, and that we were old but not like uncoolly old.
Right.
We were still like,
Right.
we were all right.
Right.
Like, what age
When did
is
that
I'm just talking about to fit, to fit through 18.
Yeah, it's like peer to
like
peer
they-
almost, right? It's
Yeah.
like an older sibling, not necessarily.
Yeah, they still think we're adults, which we aren't. But but
It's more of a role model.
yeah, I think that they enjoyed that we obviously cared, but then we also had something cool for them to do.
Yeah, yeah, great, thank you.
Just to add, I think the interaction we had, so we give our presentations and then we let them loose with the design challenge, and the interaction that happened then, like helping them through their like difficulties with the challenge and everything, is where we really built our relationships. Like we learned their names, and like I think it was really surprising for a lot of them that we remembered their names.
Yeah.
Cool.
And while they're thinking something through, it was like no bad idea. It was like, wow, yeah, that's a good one. But think about it, you know.
Right. And it's like we're working with them. It's not like we're an instructor saying yes, no. It's like
Yeah,
we're
right,
building
wrong.
off what they say. Well, what do you think about this? Or
Yeah.
you know.
Right, like you had said with the styrofoam melting in some cases. And, yeah, terrific. Great, thank you.
Hi, my name's Roland. I'm going to tell you about the self-plane challenge, where we are going to make this plane invisible to the radar. So first, let me tell you a little bit more about what that means. If you have ever seen one of these before, perhaps at an airport, then you have seen a radar. A radar works by sending radio waves out in all directions, and when those radio waves hit a plane, they reflect back to the radar. However, sometimes the planes would rather not be seen by the radar, like when our Air Force pilots are flying missions. To not be seen by the radar, planes are designed to appear smaller than they actually are, and at the Electroscience Laboratory, one of the things we research is how to do this. One of the simplest methods used is to use certain shapes and angles. For example, a sphere or a cone will reduce the amount of radio waves reflected back towards the radar, while other shapes like flat surfaces and corners are avoided because they direct the radio waves straight back towards the radar. However, if the flat surface is an angled ray, it can reflect most of the radio waves away from the radar. Another method is to use different materials because some materials absorb the radio waves while other materials will reflect the radio waves. Okay, so now that we've learned how radar works, let's identify the problem. We want to make this fighter jet invisible to enemy radar so that it can fly missions safely. How are we going to do this? Well, we need to design a way to modify it so that it doesn't show up on the radar. For my first design, I thought to use aluminum foil on angled surfaces so that the radio waves might reflect away from the side in front of the airplane, which is the sides we're going to test in this challenge. Let's see how that might look. Once we have our first design ready, we can build it. Alright, now that we have our first design built, the last thing we need to do is test it. To test your fighter jet, we're going to use light because light behaves the same way as a radio wave. So the first thing you need to do is set your fighter jet in the box with the side that you want tested facing the flashlight and centered with the flashlight. The next thing you'll do is put on the top of the box. Once the fighter jet is enclosed in the box, make sure the flashlight is turned on, and then, using a light meter app on the smartphone, insert the smartphone above the flashlight and record the lumens that are reflected back towards it. Then, repeat the same procedure for the front of the airplane. recap what we just did. We first identified the problem. We then designed a solution for that problem. We built the design, and lastly, we tested it. We made it good. Now can you make it better?
Wow, good
I'll adjust the volume a little bit.
Yeah, no, that would be a benefit, but not to say the other ones were not up to snuff, but that was content-wise one of the best ones I've seen.
I like it.
I thought it was really, really good.
Alright, yeah, so we'll go through this real quick. The basic idea, radar, making a plane look smaller radar is kind of it's a military-only application, so I kind of went with the, keep your pilot safe from the enemy radar approach with the mission statement. So that's kind of their goal.
America's enemies.
Yeah.
Your design challenge.
We should have had you narrating that video.
Wow. For the most part, I kept to their template pretty well because they like it and they're the customer. So I kept with that. On the last page, I did a SolidWorks drawing of the box I made. Just hopefully that's clear enough. I mean, it's a pretty simple thing to do. So hopefully whoever uses this in the future can make it without too much of an issue. But yeah, so I like this challenge because especially more than the kind of challenge, because it's it really is open-ended because there are a lot of different combinations that could be tried to reduce the radar cross-section. I kind of made one. This one, it did okay, but obviously there's gonna be a lot of light reflected back though, so it would have failed, and they could have definitely improved it. So the way I ended up doing this, the final setup, is when they'd set it in here, and then from talking in class, I added this part to the back so that my smartphone can just fit in this slot there, and they can measure it. I think all smartphones probably have that app. Mine, unfortunately, like the sensors on the front of the phone, so you kind of have to tilt it to read it. But iPhone and a lot of the other Droids, the light sensors on the back side. So that's the test setup. So like you guys said, the biggest takeaway for me from this class was the communication skills, because in my research lab, I present my research weekly, and I've had to present to rooms full of PhDs, and I've had to try to make them like me and make them think they spent their money well and stuff like that. And that's never been an issue, but as I appreciate from this class was the difficulty in explaining what we do to non-engineers. That was definitely one of the biggest challenges I had, and I like to think that the kids understood most of what I presented pretty well, so that helped a lot. But that wasn't the reason I did this class. The biggest reason for me was when I grew up from the area I came from, I definitely had no clue what an engineer was. My school wasn't the strongest science backed, so I like this opportunity because I was able to help students that were kind of in a similar situation learn about engineering young, because that's something I wish I would have had the opportunity to learn about. Yeah, that's pretty much it.
Yeah.
All right. We got 3 left, I believe.
4.
4?
Yeah.
Grant, Elsa, Molly, and Ben. All right, Grant, you're up.
You have been chosen.
Thank you.
Sorry, Ben. We're in the loop. Now you
Took
are.
off the bow tie, huh?
I did. It was tied weird.
That's crazy about that.
Did it. I think they're off the bounce.
Are they ours?
I don't I'm not starting that rumor either.
There's a
Excuse me, I heard you started a rumor.
Look at how not
Molly.
You just disappeared. We don't know.
I'm actually not.
You just gotta go big with it. Like, come up and like, be like,
That's fine.
I hope this comes off.
Just lift him up by his bow tie.
I thought it was coming up. I thought it was.
I will take that.
Sir?
Thank you.
Alright, so I'm gonna be different and start with my situational statement because my research, I had the misfortune of having a new graduate student and he ended up not liking what we were doing, so he left kind of early on. So I didn't get a super in-depth summer experience and I didn't make as much money as I'd like to make, but regardless, my situational statement is more about like, it's really what drives this project. I'll bring this over actually. So I'll just read that for you guys first. Alright. Researchers were using a new prototype of a spelunking robot to explore an uncharted cave on the Canary Islands of Spain when the robot malfunctioned. The robot is now stuck deep in the cave. The robot is far too valuable to leave. The researchers must retrieve it. Unfortunately, the cave is too narrow for humans, and it is full of carbon monoxide, so a trained retrieving dog won't work either. The researchers have decided that a magnet is the best way to retrieve the robot. However, the cave is full of iron deposits. Iron is a ferrous material, and it will attract a permanent magnet before it has the chance to reach the robot. The researchers therefore decided they should design a device with an electromagnet attached to the end of the robot. This should work since an electromagnet can be turned on and off. Can you help the researchers design the retrieval device? So that's what we're going off of. Right, if you want to put the video.
Trained retrieving dog.
Some smart aleck kid.
Hi, my name is Brandon. I'm a college student studying electrical engineering. Over the summer, I worked in a research lab that used electromagnets to move small magnetic beads. An electromagnet is like a normal magnet, except it only works when electricity is running through it. This means we can have much more precise electromagnets because we can change the current, which also changes the magnetic field. It also means that we can turn the magnet on and off, which you can't do with a normal magnet. So, how do we build one? Well, it's actually really easy. All you need is a nail like this. I have an iron nail. A steel one would work, but not as well. And some copper wire like this. And all you want to do is wrap the wire around the nail as many times as you can, and as tightly as you can. Alright, when you're done, it should look something like this, and that's your electromagnet. So let's
Alright, so here you can see that I have my electromagnet hooked up to the battery, and I just used alligator clips to hook it up. And it does not matter which way you hook up your electromagnet. So now I'm just going to touch it to this bent up paper clip I have here, and it'll pick it up.
So now that you know how to build an electromagnet, you might be wondering, what are they used for? Well, they're used in junkyards to pick up metal. Or in a CAT scan to take a picture of your brain. Or today we'll be using an electromagnet to retrieve a lost robot. The robot was lost in a cave, and we have to use an electromagnet because there's iron deposits, so a normal magnet would get stuck on the way in.
So here we have our cave. And actually, the cave is just a box with some vinyl tubing cut out and shaped into a S curve. And I have this clamp here to represent the iron deposits that a normal magnet wouldn't be able to